Hello everyone, welcome back to our subject Computer Organization and Architecture. So in your third unit first half we have seen about processor fundamental concepts and executing the complete instruction in single bus organization, multi-bus organization, and also we have covered about control unit design by means of hardwired and microprogrammed. Okay, and the remaining half of your third unit discuss about pipelining. So it's nothing but increasing the performance of the processor. Okay, it's quite interesting topic, pipelining, and we'll straight away get into this topic, basic concepts of pipelining. So pipelining, I think we have covered earlier in our first unit. So what pipelining is, it's nothing but overlapping of the instruction so as to execute more instructions in a given clock cycle. Okay, so it's formally defined as a means of executing the machine instruction concurrently. Concurrently in the sense overlapping the instructions. When we overlap, we could execute more instructions. In this way, we could increase the speed of the program. Okay, it's mainly it is used in almost all modern process, and pipelining improves system performance in terms of throughput. So throughput in the sense when it says about the number of instructions gets executed per clock cycle. So how many instructions we are able to execute it in a given clock cycle. So pipelining, so we are not concentrating on speeding up a single instruction execution. Instead, we are concentrating on more number of instructions. When we execute more number of instructions, so in that time only the process speed up, we need to give more concentration, is it not? So when we are executing bulk of instruction, and that too it should be executed in shorter duration, so there applies the pipeline concept. Okay, and implementing the pipeline requires some sophisticated compilation techniques. Okay, and the basic concept, it says about how to increase the speed, how to execute the instruction in a fast manner. Okay, so either we could achieve by means of designing the processor and the memory using the latest circuit technology, or by arranging the hardware components in such a way that more than one operations could be performed. And this second point we are going to deal it via the pipeline concept. Okay, yes, here in pipelining, the number of operations performed per second is increased even though the elapsed time to perform a single operation is not changed. It means, so if a single operation takes 1 second, one clock cycle, means we are not going to reduce that one clock cycle as half a clock cycle or something like that. That's not happening. Instead, in a clock cycle, we are able to execute more than one instruction. That's the logic behind the pipelining. Okay, so let's before discussing about the more about pipelining in technical manner, let's have a traditional pipeline concept. So here the analogy is given related to laundry. Okay, four people, Anu, Bala, Kaveri and Dano, so who are in a line to wash their clothes, and later they'll need to dry it and folding it. Okay, so let's have a scenario like washer takes 30 minutes to wash their clothes, and dryer will take 40 minutes to dry up, and finally the folder will fold all the clothes in 20 minutes of duration. And we will see, so if the thing happens in a sequential manner, how long it takes to complete all the four people. Okay, and see here, so taken time duration. If A, Anu starts washing their clothes at 6 p.m. So what's happening? In a sequential laundry, it takes a long time. So how it takes a long time? Let's see here, Anu. So she has the washer for 30 minutes duration, then dryer for 40 minutes, and folding 20 minutes. So totally 1.5 hours it take. Then after completing 1.5 hours, B will start its operation, then C, then D. So totally it will take, each person takes 1.5 hours, means totally 4 persons will take 1.5 into 4 is 6 hours. Okay, so this is the sequential laundry is more time. So think of it in an alternate manner, like pipelining. So the pipelining is nothing but when the washer is done, and B will immediately take control of the washer, okay, while the dryer is processing Anu's clothes. B can start washing the clothes using the washer, is it not? When the dryer is over, B could make use of this dryer, and C could make use of this washer, since the washer was free after B, is it not? So that's the concept of pipelining, and see here how that pipelining concept is achieved. Okay, so the previous question, there is one question: if the pipelining concept is used, how long would they take to complete all the, how long all 4 will take to complete? So see here, in sequential it took 6 hours. And any guess, will you able to give the answer? I'll pass some minutes and get back to you. And of course, so using pipelining concept, see here, so this picture will clearly explain you more about that. So when the user A is using the washer, so user B cannot use the dryer, is it not? So the thing has to be done in a sequential manner, is it not? For washing the clothes, it needs to go washer, dryer, then folding. We cannot go for drying without washing, is it not? So when A is in washing, B has to wait for 30 minutes till this washer is done by A. Then when A goes to the dryer, B can utilize that washer, is it not? Likewise, it's overlapping. The operation is overlapped, so that execution will be fast. Okay, so see here, the time duration is given. When A starts at 6 p.m., what's happening? It will take 30 minutes of duration to complete washer. So it will A will take 6:30 to complete washer. Then what will happen after 6:30? So B will come in place. B will utilize that washer. So at 6:30 B will start washing its clothes, and it will take 30 minutes. So totally, so B will complete washing it at time 7. So simultaneously at 6:30 A will start doing drying. Okay, so they will put the clothes in dryer, and dryer takes 40 minutes of duration, is it not? So from 6:30 to 7:10 A will utilize the dryer machine. And see here, after 7, what's happening to B? Whether B will go for folding? No, B is waiting for the dryer, but the dryer is currently engaged by A, is it not? Only at 7:10 the dryer will be free. So 10 minutes it will wait, is it not? B will wait for 10 minutes of time, that we are saying in technically in pipelining called as stall. Okay, I'll get back to you that stall term later. And just assume here now B needs to wait for how long? 10 minutes B wants to wait. Why? Because dryer is not free, so dryer is currently engaged by A. So from at 7:30 dryer will be free. So what's happening at 7:10? B will utilize that dryer, is it not? So it will take 40 minutes of time to complete. So totally B will take 7:50. At 7:50 B's drying is over. And see here, after 7:10 by A, it will go for folding it. So the folding takes 20 minutes. So 7:10 to 20 minutes is 7:30. So at 7:30 A finishes its washing. And see here, B. So B at 7 o'clock, it releases its washer. So C will occupy the washer immediately. Okay. So at 7:30, C will be finished washing the clothes and will be waiting for the dryer. But the dryer here is occupied by B. So it will take, so B will wait how long? 20 minutes it will wait, because only at 7:50 the dryer will be left free by B, is it not? At 7:50, so it will start occupying, C will start occupying the dryer, and it takes 40 minutes of time, is it not? So 8:30 it will be free, and it will complete the folding, and folding by B at 8:10 and C at 8:50. Similarly the thing goes, and at 9:50 all four operations are done. So this is how a traditional a simple example related to pipelining is given for using the laundry machine, and we will apply the same concept for executing the instructions in modern computer systems. Okay, the same concept is applied so as to speed up the operation. Can you compare the previous sequential and this pipelining? Previously it took 6 hours for all the 4 people to complete the operation, whereas here it is reduced to 3.5 hours, is it not? Okay, so pipelining doesn't help a latency of single task, it helps throughput of entire workload. What does it mean? So it doesn't help latency, it means it is not working for a single laundry, is it not? So mainly it is for more than one laundry, then only you could able to achieve the speed. You could compare the speed of completing the operation. So mainly the throughput, in the sense for how many laundry or how many instructions the things are doing it quickly. Okay, pipeline rate is limited to slowest pipeline stage. Yes, of course, we have seen the pipeline rate limited by slowest. In the laundry example, we have seen the dryer is the slowest one, because it takes for more time, 40 minutes 40 minutes time to complete its operation, but whereas washer takes 30 minutes. So once the washer is over, B is by B waits for 10 more minutes to complete this lowest stage. Excuse me for that. And so the pipeline rate is limited by the slowest pipeline stage, and multiple tasks operating simultaneously using different resources. What does it mean? Multiple tasks operating simultaneously. Yes, multiple tasks in the sense washing, drying, and folding using the different resources like a dryer, washer, and the folder, is it not? And the potential speed up of the pipelining is mainly depends on the number of pipeline stages. So if there are 2 stages, means the productivity will be doubled. If it is of 4 stages, means the productivity is increased by 4 times. Okay, and of course there is a little drawback, like if everything goes smooth, then that's it, we could achieve the speed of the operations in a right way. But in practical, it's there may be some hurdles, like unbalanced lengths of pipe stages reduce the speed up. For example, if something if while washing, if the washer is if washer when broke down or something happens, so the speed up operation is definitely reduced, is it not? Or sometimes instead of taking 30 minutes, if it due to degradation of that machine, if it takes 35 minutes, means of course the speed up will be degrade, is it not? So time to fill pipeline and time to drain also reduces. It means, so here in laundry analogy, so once washer is done, we need to move the clothes to dryer, and once the dryer is over, we need to so move the clothes to the folder, is it not? So some movement, due to that movement the performance also reduced. Okay, the stall for dependency, it means it is in the previous slide we have seen B is depending for a dryer, but dryer is occupied by A, so that 10 minutes of duration is said to be stall. Okay, and we'll move the same concept, apply everything what we have seen for the laundry example for the instruction execution. That's said to be pipelining in computer system. Okay, and sequential operation is given here for mainly if you want to execute the instruction means here we have given two stages. One is fetching the instruction and executing it, is it not? So that is represented by F and E letters here. F1 means fetching the first instruction and execute the second instruction, I mean execute the first instruction. So it takes two stages. So the instruction 1, once it is over, it goes for the second instruction, then the third instruction. So totally it takes, suppose each and every stage takes one clock cycle, okay, one clock cycle or one clock period, both are same. So for to execute this 3 instructions, we need 3 clock cycles, is it not? This is a sequential execution. And so if we rearrange the concept by overlapping it, so overlapping in the sense each and every have instruction fetch in separate unit by the computer and the execution by separate unit. Okay, so here is the hardware arrangement for pipelining. Okay, so there is a separate unit for instruction fetch. It keeps on fetching the instruction, and the fetched instruction is moved to intermediate buffer, so that we are saying as an interstage buffer. Okay, and once the fetched instruction is moved to B1 buffer, and this instruction will unit will go and fetch the next instruction. It keeps on doing it. It does only the fetch operation, and what the execution unit will do, it keeps on executing the instruction by fetching it from this buffer. Okay, so B1 always gives the input to execution unit, and it starts executing it. While it is in execution, this will be in fetching. Okay, so that we are overlapping it. So when the instruction 1 is executed here in the execution unit, and the fetch unit won't be idle. Okay, instead the fetch unit will start fetching the second instruction from the memory or somewhere else. Okay, so this is the concept behind overlapping, and the same thing is given here. Pipeline execution is given here. Okay, so overlapping, visually you could see what's happening on each and every clock cycle. So the clock cycle is given as first clock cycle, second, third, fourth. Likewise, when the first instruction is fetched at clock cycle 1, and that instruction is will take one more clock cycle to complete the second instruction. So while doing it, the second instruction started fetching at clock cycle 2, third instruction started fetching at clock cycle 3, and overlapping it will get the execution at 4 clock cycle by all the 3 instructions. Whereas here when we go for without pipelining, it takes 6 clock cycles. So here by pipelining, the performance gets increased. How performance gets increased? By overlapping it, and we are doing it in a shorter clock cycle. Okay, quickly we are getting it in 4 clock cycle itself rather than 6. Okay, it's quite interesting. And we have seen about 2-stage pipelining, and it is not necessary to have only the 2 stages. We could have 4-stage pipelining. So 4-stage pipelining in the sense, instruction we could not straight away execute the fetched instruction. Instead, it will go for different stages. Like after fetching the instruction, we need to decode it. Decode in the sense, using the decoder, it will identify what type of instruction, and if the instruction takes operand, means that also needs to be kept ready for execution, is it not? After execution, the information will be put back into the appropriate location, either to the memory or to some registers, is it not? So this is said to be a 4-stage pipelining. And see here in the 4-stage pipelining, the instruction execution is divided into 4 steps, like fetching the first instruction at clock cycle 1, and at clock cycle 2 we are decoding the instruction 1, simultaneously fetching the instruction 2, and at clock cycle 3 these things are happening, and at clock cycle 4, so you will start getting the output on each and every clock cycle. At clock cycle 4 you will get the first instruction execution, and at clock cycle 2 second instruction execution is over. Likewise you will keep on getting it simultaneously. There we could visualize the speed up operations of pipelining. Okay, so for this arrangement of four stage pipelining, we need a hardware arrangement something like this to store the intermediate results of each and every stage in the intermediate interstage pipeline buffers. So here for four stage pipelining, we have utilized three buffers, buffer 1, 2 and 3, to store the respective output from the previous unit, like fetch unit, decode unit and execution unit. Okay, and here is a role of cache memory. So what is the role in cache memory in pipelining? So we'll see. So each pipeline stage is expected to complete it in one clock cycle. That's the thing we have seen it so far, is it not? But the clock period should be long enough to let the slowest pipeline stage to complete. So sometimes for example memory read and write we have seen, so that will take some more time to complete that operation, rather than doing ALU operations inside the processor is very high, it will do the operations in short duration, but getting the information from memory and doing that and doing calculations in the processor from that information will take some time, is it not? Mainly fetch and write will take more time when compared to other operations happening inside the processor. And I think I have covered the term called as MFC, and of course I asked you a question something like MFC, but many people googled what MFC, and most of you wrote in your exam IAE2 as MFC as Microsoft Foundation class. It's completely wrong. Okay, so I put 0 for everyone those who wrote a Microsoft Foundation class. So MFC, here we are talking about the computer architecture. Okay, so here MFC I have clearly explained to you. MFC is memory function complete. Okay, so we'll be waiting. WMFC means waiting time for this memory operation to complete either read or write. Okay, so it takes more time, of course, wherever the concept is applied, either to the pipelining or to the normal operations or to the superscalar operations. Okay, so please keep that in mind, the term MFC is a memory function complete. Okay, and see here for the third point, faster stages can only wait for the slowest one to complete. Yes, of course we have seen in the laundry process, no, the dryer and the washer, there is 10 minutes difference is there, and faster stages means the washer has to wait for 10 more minutes extra for the dryer to complete, is it not? Similarly here, if any of the stages takes more time, means the slowest the fastest operating stages has to wait till the still the slowest one gets completed. Okay, so here the role of cache memory comes here. The main memory is very slow, as I said. So instead of it, we could have the concept of cache memory within the processor, and if we store whatever the instructions need to be executed in the processor currently by the cache memory, means that this time we could avoid it. Okay, this MFC could be avoided and we could achieve fast operation. So for processing at high speed, we are going for the cache memory, and so here instruction execution happens by fetching the instruction from the cache memory, so that we could achieve fast operation. Okay, and moving on to pipeline performance. The potential increase in performance result from pipelining is proportional to the number of pipeline stages. Yes, we have seen, if we have two stages, means the execution is doubled. If we have 4 stages, means 4 times we could execute faster. Okay, 5 stages means it increases as many number of stages. So that's what the performance of pipelining is directly proportional to the number of pipeline stages. Okay, these things will go normal if all the stages takes the same time to complete and there is no interruption. But this is not so practically. There may be some interruptions, and there are the chances that some of the instruction will take more time to execute. Okay, those things need to be considered, and those things will degrade the performance of the pipelining. Okay, so that we will see with this example. For example, here the instruction 2, if it takes see here, the division operation takes more time when compared to addition or subtraction. So execution time for this instruction 2, suppose if this instruction 2 is of carrying about division operation, means it takes 3 clock cycles, 4, 5, 6, it takes 3 clock periods to complete this instruction. So what will happen, it will definitely affect the forthcoming instructions like I3, I4 and I5. See here, at stage 4 D3 is decoded, and at stage 5 it needs to be executed, but execution is happening for I2 is not yet completed its execution. So what does it mean? D3 has to wait till I2 completes its execution. So it completes its at the cycle clock cycle 6, and clock cycle 7 only I3 gets executed, and this is said to be the stall. Stall means some of the pipeline stages are idle, or it does no operations. Okay, so due to some of the issues like this, here I2 takes 3 clock cycles to complete the execution operation. And see here, at instruction 4 it cannot decode it, because here D3 is D3 decoding. So here what's happening, so F1 excuse me, here F3, after fetching it, the fetched information will be placed in B1 buffer, and B1 buffer is given as an input to the D3, and D3 is the decode output will be moved to this B2 buffer, is it not? And B1 buffer is free. So that's what I4 will fetch the instruction, and fetching is over, and after the fetching is over, the B1 will hold its information. Okay, I4's fetched instruction is in B1. Okay, and at clock cycle 5 I5 cannot fetch it. So why it cannot fetch it? Because B1 is not yet completed, is it not? I4 is not yet executed, so it will wait. I5 cannot fetch the instruction at clock cycle 5. Okay, so only after B1 is set to free, so I5 can fetch it, is it not? Because B1 is that buffer is not yet processed, so everything gets stalled. Okay, so this is how the if any one of the instruction takes more cycle to complete, means the remaining units gets affected. Okay, and some of the terms involved in that stall is said to be here. As I said, stall is nothing but an ideal time. Okay, so any condition any at any stage, if some instruction takes more clock cycle to execute at any stage, means so that is said to be a stall. Okay, stall is nothing but it forces the other immediate instructions to wait. Okay, so any condition that causes a pipeline to stall is said to be a hazard. Okay, so you please give more importance to this hazard, because in the forthcoming topics we are going to deal about a hazard in detail. Okay, hazard means any condition that causes the pipeline to stall. Okay, stall means no operation is done. Okay, it makes the other instructions to hold, or it will put into wait or idle. Okay, data hazards. There are different categories of hazards are there, and data hazard is nothing but any condition in which either the source or destination operands of instructions are not available at the right time is said to be data hazard, because at the execution stage it requires operand values, is it not? If the decode stage is not able to get the operand value at right time, because operand value may involve cache memory fetch, and if there is a miss in the cache memory, it needs to fetch it from the main memory, so it takes more time than what we have expected to complete it in one clock cycle, is it not? That situation will delay the operation and is said to be the data hazard. Similarly, instruction hazard means, as I said, a delay in the availability of the instruction. It may be due to the cache miss. Okay, if the instruction what the processor is referring is not in the cache memory, so what will happen? Definitely that instruction needs to execute, is it not? Then again the processor will go and fetch the instruction from the main memory, and it will take more than what has expected time to complete. That is said to be the control hazard or instruction hazard. And finally, the structural hazard is nothing but when more than two instructions are in need to use the same resource. Okay, there comes the structural hazard, and I'll take you to the example. So in which situation the instruction will wait to access the same hardware resources. Okay, so don't worry about this, I'll take you to the next slide. I think we have next slide discussing about the structural hazard. Okay, so here is the example for instruction hazard or the control hazard. It means it arises when there is a cache miss. Okay, so if there is a cache miss, suppose if cache miss is happening at the instruction cycle, instruction 2 means it will take 4 cycles to complete the fetch operation. Okay, cache miss, then go and find it in the memory, fetch it. Okay, so it takes these many clock cycles to complete. So what's happening? So it forces the instruction 3 to fetch at clock cycle 6. Okay, so instruction 3 cannot fetch at clock cycle 3 because fetch operation is not completed by the instruction 2. Okay, so this diagram is represented in the alternate way, like each and every stages of the pipeline fetch and its time and its clock cycle is given here. Okay, at clock cycle 1, fetch operation of instruction 1 is complete, and at clock cycle 2 fetch operation of instruction 2 is happening, but it's not completed. It took all the way to 5. Okay, clock cycle 5 to complete it. So what's happening at time 2? So decoding is happening for the instruction 1, but after that decoding is not happening for the instruction 2, 3, 4, is it not? So decoding will happen only after the fetch is completed, is it not? So fetch for the instruction 2 is completed only at clock cycle 5. So that's what decoding is starting for instruction 2 at clock cycle 6. Okay, so likewise all the stages goes idle for 3 clock periods, and that is said to be the bubble. So bubble means idle period that will delay the forthcoming stages of pipeline. Okay, until it reaches the last unit of pipeline is right. Okay, so this is said to be the bubble. So it bubbles through the next stages until it finds the last stage. Okay, this is an alternate way of representing this instruction execution. Okay, and this is all about delay in getting the instruction. Okay, this is an example for instruction hazard. Okay, and moving on to structural hazard. As I told you, structural hazard means it is something few instructions are in need of using the same resource. Okay, so take an example. The clock period is given. So each and assuming that each and every stage will take one clock period. Instruction 1 does there is no issue for instruction 1 execution. It does that. It completes its execution at clock cycle 4. And see here, the load instruction is supposed to be of this one. load x r1 and move to r2. What does it mean? It's an index addressing mode used. What does it mean? Add this index value to this register r1. So it's given in the bracket r1. So it means r1 is having the memory address. In that memory address, add this index value. Suppose if r1 is of some value 1010 and index is of something 20, means so add the operations. We need to perform this addition. So this addition operation will be performed at the execution stage, is it not? Execution stage will do this one. So and it will give the result as 1030. 1030 is what? It is the memory address where we need to fetch the value, and that content has to be stored in R2. So that's the meaning of this instruction. Okay. See here, I2 goes smoothly for fetching, decoding and execution. So execution at execution in this example 1030 will return, is it not? So 1030 is nothing but the address of the operand. So it will take one more clock cycle to fetch the instruction, and that information is stored in the moved to the R2 register by this write cycle. Okay. So here instruction 2 takes 2 clock cycles, one more extra clock cycle. Okay. And let's see here what that structural hazard is. So I3 goes smoothly for fetching at cycle 3, and decoding is happening, execution is execution goes smoothly, and here after that execution, so it needs to write it, is it not? So it needs to write the result, and it could not do the result at this stage of 6 clock cycle, because I2 is not completed writing it. So I2 completes only at clock cycle 6. So there comes the structural there comes the stall. Okay. And I'll come back to that structural hazard. Okay. And I3 supposed to write at clock cycle 7. Okay. And I4, what's happening at clock cycle 4? Fetching, decoding is happening. And see here at I5 what's happening. Here I5, so it doesn't start fetching at clock cycle 5. Why? Can anyone guess it? There comes the concept of structural hazard. Uh, can anyone guess it? Why F5 is not happening here? Fetching is not happening at clock cycle 5. So fetch means what? How to get it from the memory, is it not? But see here, memory operation is happening for the instruction I2 at clock cycle 5. So see here, I2 requires the memory operation, and I5 also requires the memory operation at clock cycle 5. So that is said to be structural hazard. Two instructions are competing for getting the memory resource, is it not? So then there comes the stall over here. I5 cannot fetch it over here, because I5 also needs memory and I2 also needs memory. Two instructions are requiring the same resource, same hardware resource. This situation is said to be stall hazard, and that also imposes one idle condition over here. Okay. And F5 fetching of this instruction 5 is happening only at clock cycle 6 and not at 5, and hope you understand why. Okay. And that is said to be the structural hazard. It means more than one instruction is competing for a single hardware resource, and we could overcome this structural hazard by having more than one resource. Okay. And finally about talking the performance of pipelining, as we discussed. So pipelining is not for the individual instructions. Okay. So we could compare its performance only when there are large number of instructions has to be executed, and its performance is computed via throughput. So throughput is nothing but the number of instructions executed in a clock cycle. Okay. In a 4-stage pipelining, we could have each and after cycle, starting from cycle 4 onwards, we are able to execute each and every instruction in a single clock cycle. And at clock cycle 4, so I will take you here. See here, So previous example itself, so far here there is no issues in the structural hazard. So see here at clock cycle 5, what's happening, instruction 1 is writing its output, execution happens for instruction 2, decoding happens for instruction 3, and fetching happens for instruction 4. So all the 4 stages are happening at a single clock cycle, that is by means of pipelining. Okay. So throughput, as I said, is measured by the rate at which the instruction execution is completed, and some of the issues involved in pipelining or pipeline performance is degraded due to some of the hazards and stall. Okay, so we need to identify the method to resolve the hazards and to minimize the impact of degradation in pipelining, and those things we are going to discuss it in the next topic. Okay, so that's it about pipelining. I hope you enjoyed that concept because it's quite interesting, pipelining. Okay, so how modern computers utilizes the pipelining concept to speed up the operations, and of course while implementing the pipelining there comes some of the issues we have seen in this topic, hazards, and how to overcome those things. We'll see it in the next topic, and based on today's discussion, just complete this quiz and post it in the Great Learning. Okay, 4 instructions are there, and instruction 3 takes 2 clock cycles of execution, and assume the other instructions are taking only 1 clock cycle for each and every stages of pipeline. Okay, so instruction 3 alone takes extra 1 clock cycle for execution. So for this, just draw the 4 stage pipeline and figure out how many clock cycles it take to complete all 4 instructions. Okay, that's it about today's topic, and I'll meet you in the next topic. Till then, thank you all.